Someone confirm if you are hearing me clearly. Is everyone hearing me clearly? Okay, I also need someone to talk to be able to see if I can hear you by talking as well.
Hello.
Oh, okay. Thank you so much. Thank you for confirming that. Okay, so I want to welcome everyone to our final revision class today. Of course, before now, I send a message that, of course, this class is, the revision class is going to be held remotely to give a student opportunity, to be able to attend from the comforts of their home. So, I also want to say that today I'm going to give a kind of, or let me just say, information about how the final exam, how it's going to be. Of course, before now, I've already sent a message about the area of coverage in the final. I need you to check, um, the announcement section for that information. I'm talking about exam guide, the final exam guide. So, going by the final exam guide, of course, you know, exam two is very, very critical. And assignment 8, 9, and 10 are very, very important. So I also need you to revisit the solution to assignment 8, assignment 9, and assignment 10. Now I've already, let me see, I think I've posted um, solution to exam 2, which you can actually check that on Canvas. The solution to exam 2, okay, it's already published. It's on week 15, module 15 on Canvas, okay, because areas in exam 2 are also very, very crucial, okay, as far as final is concerned. So what I'm going to do today and Wednesday is to walk you through the areas that will be covered in the final, okay. I'm going to say this again. Um, exam 2 solutions, very critical, okay. Assignment 8, 9, and 10, also very critical. If you want to go by exam, the final exam guide that I released earlier, I said, of course, chapter 9, 10, and 11. Okay, so the chapter 9, 10, and 11 are very, very crucial. And of course, I can confirm to you what you're going to see in the final. I think a chat came in now. Just check. Somebody said that we allow any cheat sheet on the final exam. Yes. Okay, you allow two cheat sheets one-sided or single sheet double-sided. Okay, and don't forget the final exam is going to be held in person in that same class. It's going to be held in person in that same class. There's no online, okay, for the final. It's going to be in person. Of course, the university they decided on the final at the beginning of the semester. Okay, now um, the final exam, we have the knowledge of efficiency tested, sufficiency, okay? I mentioned efficiency, sufficiency, also consistency. Then what about method of estimation as well? The method of movement, the method of maximum likelihood. And not only that, what you're going to see as part of the final, Chapter 11 is very, very crucial. That we call linear model. Okay. But I'm actually going to walk you through this material now. And the final practice, give me 1 second. I want to see if I've also uploaded this final practice as well. Okay, the final practice is not yet, I mean, this particular final practice is not yet uploaded. So what I'm going to do right now, I'm actually going to I'm going to upload that right away on the canvas for you to see. Okay. Give me 1 second. I think I'm actually doing that right away. I'm doing that right away now. So like I said, the solution to exam 2 is on canvas. I uploaded that. You can check with week 15. You're actually going to see that. And right now, I think I just uploaded the final exam practice. This particular material now, you can check on the canvas. So I've uploaded that. So you can find out on the week 15. So let me first start with this. Of course, this is part of the question that was set as part of exam 2. Okay, you're given a problem like this, and of course, you know, this is from a uniform distribution where you have a theta cap, you got to estimator. Okay, and of course, as part of the theta cap 2, you got a yn, which is the maximum order statistics. Okay, and they ask you to figure out the efficiency of theta cap 1 related to theta cap 2. Okay, now I told you the other time, if you want to figure out, if you want to talk about efficiency, if you want to investigate efficiency, you need to be able to derive the variance of the estimator. So which means I need to derive the variance of estimator theta cap 1. I also need to derive the variance of the estimator theta cap 2. But don't forget, the theta cap 2 here is actually if it's a function of the maximum order statistic. And if I want to start right now, okay, so I want to for derive the variance of the estimator of theta cap 1. Okay, and that's exactly, if I want to derive that, I need to be able to understand what is the variance of a random variable y that actually follow uniform distribution. Okay, now you got a uniform distribution with A equal to 0, B equal to theta. And of course, as far as a uniform is concerned, the expectation of Y is actually B plus A over 2. And of course, the variance of Y, okay, is actually B minus A all squared over 12. Okay, now in this situation now, based on the interval given, your A equal to 0 and your B equal to theta. So the moment you plug in 0 plus theta divided by 2, that will give you theta over 2. Okay, and that was why here we said the expected value of y is theta over 2. And of course, when you make use of this guy here, okay, b minus a all squared divided by 12, you plug in theta and 0, that's going to give you theta squared over 12. Now, before you can derive either the expectation of a theta cap 1 or you derive the variance of a theta cap 1, you actually need to know the mean and the variance of the parent distribution. Now, take a look at this now. I want to find the expectation of the theta cap 1, and of course, theta cap 1 is 2y bar, so 2 is going to come out, so I'm going to have expected value of y bar, and don't forget, expected value of y bar is the same thing as the expected value of y, okay? And the expected value of y here is actually theta over 2. So by the time you do 2 multiplied by theta over 2, that is going to give you theta. And for you to be able to get theta here, it means theta cap 1 is an unbiased estimator, because the expected value of theta cap 1 is actually equal to theta. Now, I want to get the variance of theta cap 1 now. So the variance of 2y bar, of course, to come out to square, that will be 4. Variance of y bar, okay? And of course, when I talk about variance of y bar, okay, the variance of y bar is the variance of y over n, okay? And what is the variance of y? The variance of y here is theta square over 12. Okay, so by the time you do 4, okay, and theta squared over 12 over n, by the time you simplify that, that will give you theta squared over 3n. And that is how we derive the variance of theta cap 1. You know the reason why we're doing this? Because the question asks about relative efficiency. And if you want to talk about, want to figure out relative efficiency, I actually need to derive the variance of the estimator. Is there any question about how the variance of theta cap 1 is theta squared over 3n? Is there any question about that? Is there any question? Okay, I want to confirm again if you are still hearing me clearly. Is everyone still hearing me clearly? Okay, thank you so much. Thank you for confirming that. Now, I want to go into deriving the variance of a theta cap 2. And of course, there's something I need you to take note, okay? You know, as part of the theta cap 2, there is a y, maximum order statistic, n plus 1 over n is just a constant, and the maximum order statistic is a random variable. Then I need to be able to recall the formula for the maximum order statistic, okay? So if you take a look at, this guy now, give me 1 second. Okay, if you take a look at the formula of maximum order statistic, we actually going to use that to get both the we need the variance of yn, but there's no way we're going to get the variance of yn without getting the expected value of yn. So if you take a look at this guy now, that is the formula, okay, for the distribution of maximum order statistics. You can see the formula right here. And of course, we started plugging in what is the CDF and what is the PDF. The PDF is going to be 1 over theta. The PDF is 1 over theta. You don't forget, for uniform distribution, it is 1 over b minus a, and b here is theta, a is 0, so it's going to be 1 over theta, and of course the CDF is y over theta. By the time you plug that in, you get that distribution. The next thing you actually going to do is to obtain the expected value of yn. Now the expected value of yn actually give n over n plus 1 theta. And of course, the moment you get that, you can now try to investigate whether the theta cap 2 is an unbiased estimator. Okay, and at the end of the day, we can see both the theta cap 1 and the theta cap 2 are unbiased estimator. Let me tell you this, when a question is asked about their efficiency, you do not need to investigate for unbiasedness. But except that, the one that involves the maximum order statistics, there's no way you will be able to get the variance without first taking the expectation. Don't forget, we are actually putting into consideration the maximum order statistics. And of course, I'm actually going to do that guide, and the end, I get the variance of yn. And after getting the variance of yn, then I can actually, but don't forget, initially the theta cap 2 was actually n plus 1 over n yn. So if I take the variance, okay, if I take the variance of both sides, it's going to be n plus 1 over n all squared variance of yn. And of course, the variance of yn is this guy now. Okay, so that is what, and this guy is the one I call the square. You put that guy in, you simplify, algebra is very, very important. And right now, you're actually going to get this as the variance of theta cap 2. Now you've gotten the variance of theta cap 1, you've gotten the variance of theta cap 2, and all what you're just going to do is to find the ratio. So don't forget, they ask you to find the efficiency of theta cap 1 relative to that. You can do the variance of theta cap 2 divided by the variance of theta cap 1. Okay, so I need you to take note of that. Okay, now, is there any question about, I think I'm done with that, probably in the exam, if you're actually going to have a question on relative efficiency, okay, so when you have a question on relative efficiency, okay, all what you just need to do is to figure out what is the variance of the estimator, okay, then you now do the ratio. So the variance of one of the estimator could be a function of a maximum order statistics. It could be a function of a minimum order. And of course, there's possibility that, what if any of the estimator is not a function of either maximum or minimum? Of course, that would be super easy. Okay, so another area that will be tested in the final is actually called sufficient statistics. And of course, if we want to investigate for sufficiency, the idea of the factorization theorem, okay, Fisher-Neyman factorization theorem is what I actually required. Okay, so that is what I want you to, if you take a look at this question now, if I were you, you can try common probability distribution in statistics and trying to investigate how, for sufficiency and all what you just need to do. Okay, if you really want to do that, give me 1 second. I think I'm going to take the picture of the distribution now so that I will be able to use give me 1 second so that I will be able to use my whiteboard. Okay, so that I will be able to use my whiteboard. Okay, so take a look at this distribution now. Okay, and they want you to investigate for sufficiency. In fact, they want you to show that this guy is actually a sufficient statistic. Okay, now I'm going to stop my share right now. And I'm going to share my, my whiteboard. Give me 1 second. Okay, so I need every one of you to confirm if you're seeing my whiteboard. Does everyone see my whiteboard? Thank you so much. Thank you for confirming that. Now you are given the distribution with the density. You got theta 1 over y plus 1 raised to power theta plus 1. And of course, y is greater than 0, theta also greater than 0. Of course, when you are given any probability distribution and they want you to investigate for sufficiency, all what you just need to do is to obtain the likelihood function of that distribution. So what I'm going to do right now, I'm actually going to have this of that f of yi, okay? I'm actually going to put a product, okay, theta. Then I'm going to have 1 plus this raised to power that, okay? And you know what? What this guy means now is that I'm actually going to have this guy to theta, and I'm also going to have a different one, okay, I can split this guy down into this, and I have another one that's into 1 over y plus 1. Take a look at that. So when you take a look at this guy here, okay, it's more or less going to be theta raised to power n. Okay, now we take a look at this guy now. Okay, 1 over y plus 1 theta. Okay, and this guy now, okay, 1 over y plus 1. And when you take a look at this guy, you take a look at this guy, we've been able to simplify, factorize that into two functions in such a way that one is independent of theta and the other one is not independent of theta. You're going to look at this guy now, h of y, and of course, this is the one that actually possess theta. And of course, here we can actually say, okay, pi, the product, 1 over y plus 1 is sufficient statistic. Okay, so we've succeeded in showing, what they asked us to show right now. Okay, so which means in the end, you can just say, okay, t is now equal this I start from 1 to n, 1 over this plus 1. Okay, which is sufficient statistics for theta. Okay, so that is how. So all what you just need to do is you need to practice for this every distribution we've done. Okay, how you can actually obtain sufficient statistic. Okay, all what you just need to do is to get the likelihood function, which is going to be the joint probability density function. Okay, now when you get the joint of that, then see how you can factorize that into two in such a way that a function is going to be independent of theta and the other one is actually going to have a theta in it. And of course, you've succeeded in figuring out the sufficient statistic. Is there any question on this? This is also being recorded. And of course, I'm going to share the link at the end of the day. And I also want to use this opportunity to tell everyone all our lectures, they have been, and I've been recording them. So you're actually going to have access to them. Of course, when you check my YouTube channel, you're going to see them. Okay, so I'm gonna stop my share now in the absence of question. Since there's no question at this time, I'm actually gonna go back to the uh, you know the uh, practice or exam questions. Then I'm gonna share that again. Okay, now we've done relative efficiency. We've also done sufficiency. Now we want to move right now to the next question. Okay, so in the part two, part one actually, part one actually tested days, and of course, in the part two, okay, it also tested the knowledge of sufficiency as well. Okay, you have a distribution given as days. Okay, you can see the distribution right now. Okay, so this is the distribution. Okay, now they also wanted to find a sufficient statistic for beta. Okay, so how do I obtain a sufficient statistic for theta? I'm also going to use the idea of Fisher-Neyman factorization again for the question. Now, if I want to use the knowledge of, Fisher-Neyman factorization for the question, it means I actually need to get what I call the likelihood function of the given distribution, and that's exactly, this is going to be the first step. You can say the first step, introducing that guy. Okay, so I want to have that in n times right now, and of course, you're actually going to have a product for the y, which is this guy. And of course, over beta is more or less that you have 1 over beta in n times. And that is why another way to rewrite that guy is going to be that, you have that. Take a look at that. Okay. And of course, wherever you have an exponential function and you want to write that's in a joint form, okay, then y is going to attract summation sign. Don't forget, okay, when you have an exponential and you got an exponent on the exponential and there's a variable, if you want to write that in a joint form, of course, or instead of, this guy is going to have a summation y squared. Take a look at that. Now, I think so far so good, right? Up to this junction. Now, in order for me to simplify, okay, I can just, okay, summation y squared here is the same thing as u. Okay, maybe u or t, you can use u, you can use t, or equal to that, right? Now, when you take a look at this guy now, okay, you're actually going to see the parameter is beta, right? If I want to rewrite this guy, if I want to factorize that guy, I'm actually going to have beta raised to power minus n exponential raised to power negative days over 2 beta. And of course, I'm going to have this guy. I start from 1 to n yi. Well, now when you take a look at this one now and this one now, you're actually going to see we've succeeded in factorizing the two functions, the joints, PDF, which is a likelihood function into two functions in such a way that one, a particular, here has the parameter, and of course here does not have the parameter. Let me tell you, where you have the parameter is where you're going to have the sufficient statistic. Here now, this is where the parameter is, right? The sufficient statistic is going to be part of where the parameter is. So which is going to be u equals summation yi squared. So I'm going to say that again, where the parameter is where you're actually going to figure out where you're going to locate your sufficient statistics. Okay, so take a look at that. This is how that is done. Is there any question? Is there any
Uh,
question about how that guy is being derived? Is there any question?
I had a question.
Okay, go ahead.
In the in the exponential under, why didn't 2 beta also get the summation to n?
Because the beta is not going to get a summation because the beta is a parameter that is fixed. So
But
beta, a parameter is not subject to variation.
we do that with beta for yi over beta. We did that for the normal variable, not outside the exponential.
Yeah, actually, I understand what you mean. If you take a look at this guy now, okay, if I have exp minus yi squared over 2 beta, and I want to have this in n term, okay, if I want to have this in n term, you're going to have so many of this guy, okay, maybe you have this 1 squared 2 beta, another one y2 squared 2 beta. You can see in every one of them, you're only going to have 2 beta. But what is changing is y. Does that make sense? You're going to have y1, y1 squared, y2 squared, y3 squared. But the beta is not going to change. Okay. But when beta is alone, just like what you said here, when you take a look at this guy, where I got yi, right? And I go over beta, I can split this guy into two. I can split it into yi 1 over beta. They are separate entity. And of course, the product can go here, the product can also go here. But in the case of that of the exponential, because the exponential is carrying this already, you cannot split them into two because this is on the exponential. It's an exponent. So it is only summation, that it's only y that we attract summation. The beta there is not going to attract summation. Does that make sense?
Yeah, that makes sense. Thank you.
You're welcome. Okay, so I think so far so good, right? I've walked you through how to get related efficiency. I've also walk you through how to get you know sufficiency. Okay, now the next here is to walk you through consistency. I'm confirming to you, on the final, you're actually going to see question on relative efficiency. You're also going to see question on uh, you know, on a sufficient statistic. Then you're also going to see question on consistency. So in my plan today, I want to walk you through 50% of that. We're going to continue on Wednesday, but this material, this practice question for the final is already published. You can check the course canvas for that. Now let's take a look at problem three. If you take a look at problem three now, okay, you were talking about working with two population, X1, we got two different measurement. Okay, we got measurement X1 up to Xn from population one that follow normal distribution with a mean of mean S and the variance sigma square S, and we get another measurement y1 up to yn that follow normal distribution with a mu y and a sigma square y. And right now, the question is suggest a consistent estimator for the mu s minus mu y. Now, if you remember, if you take a look at what I have now, if I want to talk about consistency, the consistency, I also need to understand the variance of the estimator. So what consistency is talking about, when the sample size is sufficiently large, okay, we expect the variance of an unbiased estimator to converge to zero. But in a situation where the estimator is biased, then we expect the mean square error, okay, of the estimator, of the bias estimator to converge to zero. Okay, now, how do I know this guy is actually, how do I know I'm actually going to use the idea of, the variance of the mean square error? What I need to do is to first investigate that estimator for unbiasedness. I'm going to say that again. They say suggest a consistent estimator for this guy here. But you know what? I need to first understand, because I know if I want to work with a consistent estimator, I actually need either the variance or the mean square error, depending on whether the estimator is unbiased or biased. If the estimator is unbiased, then of course I actually need the variance. And what I just need, when I derive the variance and I take the limits of sample size tend to infinity, I expect the variance to converge to zero. But in the situation, if the estimator is biased, then I need anything other than variance. I need a mean square error. So then I'm going to take the limit as n tends to infinity. I actually expect the mean square error to converge to zero. But right now, let us first investigate the biasedness or the unbiasedness of this estimator for us to be able to see whether we're going to make use of the variance or we're going to make use of the mean square error. Now, because we're talking about difference of means and they all come from two normal population, okay, I want to tell you this is going to hold expected value of the difference of the sample mean is going to be equal to that, and it's going to be equal to the population parameter. Okay, when you take a look at this now, what it gives, this is a population parameter. Okay, the estimator for that is actually going to be the sample mean minus that guy. Okay, now it's going to be that guy. So take a look at that guy now. Okay, now I now need to investigate. This is the estimator. This is the parameter. Okay, this guy is the parameter. This guy is the estimator. Okay, if I want to know whether it's an unbiased estimator or not, then I'm going to do this. Okay, and of course that shows an unbiased estimator. And the moment it is an unbiased estimator, what I just need to investigate consistency is actually the variance. Now, I'm actually you remember from what we did before, take a look at that. What is the variance of x bar minus y bar? Okay, you remember the variance of this is actually going to be this guy here. Don't forget, we're told that x and y, if you take a look at the IID, okay, they are identically and independently distributed, which means we expect the covariance to be 0. Now, if that happen now, this guy is this guy, this guy is this guy. And you can see the denominator. Now we can investigate for consistency now. Okay, investigating for consistency now. We're going to take as n tends to infinity. Okay, so when you can see the way I'm doing it. You see the way I'm doing it? Now the next operation now is this guy now. I really want to investigate. When n tends to infinity, what happen? As we can see, or that guy converges to 0. And of course, when n tends to infinity and the variance converges to 0, then that estimator is actually consistent. So which means the estimator that is consistent now is x bar minus y bar. Okay, it's consistent. It's a consistent estimator for what? It's a consistent estimator for this guy. Okay, so is there any question on this? Is there any question on this? Okay, I want to ask again, is there anyone, are you see, if everyone still hear me clearly, right? I need someone to confirm if you're still hearing me. So, okay, thank you so much. Thank you for confirming that. Now we're done with problem 1, 2, 3. Okay, what I've done today, I've been able to walk you through how to investigate for relative efficiency and how to obtain sufficient statistics using the idea of Fisher-Neyman factorization theorem. And right now, I just walk you through consistency. Okay, so in the part 2, take a look at this guy. There's another question on consistency. Give me 1 second. Okay, so when you take a look at this guy now, it said let x1, s2 up to xn be IID. Okay, that follow normal distribution, with unknown parameter theta, which means the mean is unknown and variance is known. Variance is 1. You remember the specification of this guy, right? It's always this guy, right? So which means we don't know mu, but the sigma square is 1. That's what that means. And the question now say, okay, if theta is unknown, okay, the population mean is unknown, then we need information about what the estimator is going to be. And the information here, the estimator suggested here is sample mean. Okay, don't forget we want to use this sample mean to estimate the population mean. And the question now is show that sample mean is a consistent estimator of theta. And don't forget the theta here is actually the population mean. Okay, now if I want to do this, okay, I will need to first investigate what kind of estimator, okay, is X bar. Is X bar an unbiased estimator or a biased estimator? Don't forget, if you want to investigate for consistency, okay, you're actually either going to work with the variance of the estimator or you're going to work with the mean square error of estimator. Okay, so you're only going to work with the variance of the estimator if and only if the estimator is unbiased. Okay, and you're actually going to work with the mean square error if the estimator is biased. And that is what we want to start with, starting our investigation, with what is the unbiasedness property of this. So the expected value of X bar, okay, is actually going to be equal to, see what you see now, okay? And in the end, we can see it is actually theta, which is going to be mu, okay? I think in the specification here, let me see. This is supposed to be expected value of X bar, which is going to be summation X over N. I think that is, okay, summation X over N. And when you have summation X over N, summation is going to come out, expected value of X over N. This guy cancel that, so which means expectation of X bar is the same thing as expectation of X. Okay, that's another way, and that's going to give you theta. And the moment you theta, it's actually telling you, you know, the estimator is unbiased. So if the estimator is unbiased, then all what we need to investigate is the variance. So what is the variance of X bar? Of course, the variance of X bar is the same thing as the variance of X over N, right? What is the variance of that X? Is sigma squared, right? And that sigma squared has already been given to be 1. You see, it's already given to be 1. If you plug that in, that's gonna be 1 over N. Okay, so the variance of X bar now is 1 over N. Now, if I want to investigate consistency now, or what I just need to do is to take a limit as n tends to infinity. I'm just going to take the limit as n tends to infinity. Of course, when n tends to infinity, you can see n in the denominator. Of course, the whole thing is going to convert to 0. And of course, when the variance converges to 0, that actually implies that estimator is a consistent one. Okay? It's a consistent one. Is there any question? Is there any question? I'm actually going to start this on Wednesday. Okay, you know, before Wednesday, I'm going to tell you that, okay, you know what, uh, in the exam, the knowledge of method of estimation will be tested. You remember in this class, I walk you through the method of maximum likelihood, and I also walk you through the method of movement. The two of them will actually be tested as well. Or somebody said, are these files online? Of course, I've already published that. You can check the module. Okay. I need you to confirm. You can go to the module now. Go to week 15. Go to the week 15 on the module. If you can see the file right now, I need you to give me a thumbs up. For those of you online, go to week 15 of the module. Okay. If you can say, okay, thank you so much. It's already online. You know, I've seen a good number of students confirming that. So you got the material online. So like I said, you know, method of estimation will be tested as you can see right now. Okay. And not only that, assignment 8, 9, and 10 solution. Like I said, the assignment 8, 9, and 10 solution is what I pulled here. So on Wednesday, I'm actually gonna walk you through all of this, like likelihood ratio test, Neyman-Pearson-Neyman theorem, and the linear model. Okay, you know, right now the final exam is actually going to revolve around this particular practice, you know, the topics in the practice question. So like I said, I'm actually going to continue from here on Wednesday. Is there any question before I go today? Is there any question before I go today? Is there any question? Okay, so if there's no question, silence implies you really understand that. Of course, I'm gonna meet with you again on Wednesday, and that's gonna be remotely. We're also gonna meet over the Zoom. And don't forget, your exam is going to be held in person, okay? It's going to be in the same class that you normally have your regular lecture. Make sure you all stay safe and have a lovely day. Bye for now, everyone. Thank you too. Thank you. Yep, thank you.